make sure everyone's aware, and then I'll update the schedule accordingly. Oh, that's my sticky thingy. Oh. How was the quiz, you guys? Does anyone have questions from the quiz?
I hit the wrong button twice. I feel stupid.
Oh no, Becky. It's terrible.
So for like number 2 and 3, it's like they're assuming that you only put positive numbers in. Because I was thinking about like a cube root graph and how that goes up and down, but they're assuming you put only positives in n. Yeah, that makes sense.
Yeah, for sequences, we're only talking about values of n that are positive integers. Always. Mm-hmm. Yeah,
that's because, oh, sorry. Is that because like when we like kind of like evaluate like our sequences, we always n always starts at 1, right? We always go like 1, 2. So that's why we only consider positive numbers. Yeah, because I was thinking of the cube root graph too.
Oh, yeah. No, that's how we define sequences. We're only talking about values of n that are positive integers. Yes. So then you don't need to worry about the values going negative. So that's kind of a nice thing about sequences versus talking about functions. Good questions, you guys. Anything else? I mean, it seemed like the homework went well. Not everybody got to it, but it's not due for another 5 days. But some of you did it right away, and the office hour's been really quiet. So we're actually not too bad on the schedule. I was thinking we were like a whole section behind, but really I had planned in our schedule to start 8-1 last week, but I didn't realize that I had planned on finishing it tonight. Well, technically that would have been, sorry, it's confusing. We're only like half a section off, so we're not too bad at all. So tonight we're supposed to be doing 8-2 and starting 8-3, which is exactly what I'm going to do. So we're in week 10, which is the week of October 25th. So that was Monday. And then Monday, if you watched your asynchronous lecture, maybe you watched it before then, you did 8-1. Tonight, I'm going to be doing 8-2 and starting 8-3. What you'll notice is that these sections are a little shorter. 8-3 has some integration in it, which makes it a little bit harder than some of the sections that are going to follow. But what we're going to be doing after 8-3 is just a lot of sections where we'll be doing certain comparison and ratio tests and different types of things to look at what's happening with the convergence or divergence of our series. So starting tonight with 8-2, and then moving all the way through 8-6, and then 8-7 is kind of like a review section. We're going to be focusing only on talking about series and whether or not the series converge or diverge. So 8-2 is really where we're going to get into talking about what a series is, and then sort of talking about how it's different from a sequence. So if you'll remember from 8.1, I was saying in the video that you're seeing sequences in 8.1, but you're not really going to be seeing them again in the chapter. And that holds true. And then we'll sort of use these same techniques when we talk about power series in 8-8. And then if I don't get to 8-9 and 8-10, I'm not too upset about it. I pretty much never get to those. It just is the way things end up working out on the schedule. And I don't want to end up smashing chapter 9 in here, especially if we don't have that time due to Thanksgiving. That'll take out time we have on chapter 9. So it's not that chapter 9 is like super hard or anything, but the first couple sections are much easier. So it's like 6 sections. The first 3 are really pretty basic, and then the last 3 are a little bit harder, where you have to set up some integrals. Not quite what you did in chapter 6, but the same type of idea. So I don't want to rush the end of chapter 9, because you only have 3-week turnaround between test 3 and test 4. So I'll probably end up starting chapter 9 on week 13. Right before you have test 3, which I don't think will screw you up too much, because the beginning of chapter 9 is, I just want to plant those seeds, but it's not like it's super hard or anything. Okay, so that's sort of my plan going forward. I don't know. I think when I made the schedule, I was like, oh, I think I'll just maybe have them do 2 asynchronous lectures that week so I can get it in. But now I realize it's kind of cheating. I can't make you do that if it's Thanksgiving break. What was I thinking? Okay, so let's talk about series in 8.2. First of all, I'm going to define for you what an infinite series is. I feel like this whole chapter for me is kind of slow going. Well, at the start of it anyway, and then once I get into it, get really into it. So maybe you guys are already gung ho. Who knows? It's hard to shift gears from doing something like with heavy integration and then moving into something completely different. You got to kind of get into it a little bit. So 8.2 is officially called infinite series. But if you'll remember, I said that your next 2, 3, 4, 5, 6, 7, 6 sections are going to be about series. So it's not like this is the only place you're going to see it. This is sort of your introduction to series, and we're going to talk about a few different types here. And then we're going to talk more about convergent tests for different types of series in the upcoming sections. All right, so I'm going to give you first a definition for an infinite series so you know what it is. Then I'm going to give you an example of sort of how you would work with them, but you'd be surprised how much you're not actually going to be adding up terms of series in here. We're going to be doing a lot more with looking at types of functions that would be inside your series. So the definition for an infinite series if a sub 1, a sub 2, all the way up through a sub n. Sorry, I'm losing my focus here. Make it stay right there. If a sub 1, a sub 2, all the way up through a sub n, and then, you know, forever and ever and ever forward, is an infinite collection of numbers then the expression and we're going to be using summation notation here. So I'm going to use that uppercase sigma that you've, I'm sure, used before at some point. Maybe the last time you saw this was in Algebra 2 or College Algebra, whenever you had that. Your book likes to use K. I'm very used to using N. It's just what I've always used. I'm going to try to be consistent with K. Sometimes I accidentally throw in an N. So if I do that, don't be like, whoa, she's got 2 variables going on. We're only going to be sticking with 1 variable. If I accidentally use an N, I'm really sorry. I'm going to try to keep an eye on it. I'm just trying to be consistent with your book because they use Ks. All right, so this is the series or the sum from 1 to infinity of a sub k, and that is equal to a sub 1 plus a sub 2. So you're adding up here the different terms of the sequence of numbers. And then just keep on going on and on and on until you get to a sub n. Keep going on and on and on, all the way up to infinity. This is called an infinite series or simply a series. I cannot remember if you ever looked at any sort of infinite series in algebra. I want to say no. I think these always stopped at finite values, and you found summations using formulas for sums. Maybe it was even in your intermediate algebra class, if anyone took that. I don't know if that would even have been a college algebra thing. Now I'm like jogging my memory. It's been a while since I've taught algebra. So just like with sequences, a sub 1, a sub 2, a sub n, so on and so forth are terms of the series. Now, it's not a sequence. Remember that a sequence would just be if I'm just listing out the terms that are represented by the function. In this case, I'm taking the first one and I'm adding it to the second one. I'm adding that to the third one, and I'm adding all of these together. So you can see how that would create a very different value I mean, because really at the end, you're going to get one value instead of, a collection of terms. So those are your terms. And the number a sub n is called the nth term or general term of the series. Okay, so your sigma is the summation. We know that. And k is the index of summation. Some of these, I mean, we'll use terms very often, but as far as talking about an index of summation, I mean, it's good to know, but that's not really some terminology we're going to be using a whole lot of. Now, the index of your summation can begin at any integer, but we're usually going to begin at 1. The index can start at any integer. So that's going to be different than what we did with sequences. We were just talking at the beginning of class about how for a sequence, we're only looking at values of n that are positive whole numbers. In this case, we can actually start our sum at any integer. And remember, integers can also be negative. We usually start at 1. Sometimes we start at 0. Just kind of depends on the sum that we're working with at the time or whatever series that we're looking at. Okay. I will give you a sort of a rundown of what this would look like if you were to actually sort of like power your way through the series. And then we're going to talk about specific special types of series. And actually the one that I'm going to give you in this example is actually a special type of series, which I'm going to tell you about in a couple minutes. But first, I want to show you sort of the way that a series works before we get into that. Any questions so far?
Nope.
Okay, so let's see. Example 1.
Quick question though, since I
Yes,
just
go
thought of
ahead.
it. You said any index, the index can start at any integer, so they can be -2?
Yeah, it can, because I mean, think about the fact that you're really just adding up terms here. And I think as you work with more of these series, you're gonna see why where you start isn't going to affect anything. But basically what we're heading towards is, does the series converge to a value or does it diverge off to infinity or negative infinity? And you'll see that no matter where you start, the convergence or divergence is eventually going to end up in the same spot. And that's why it doesn't matter where you start it. Yeah, thank you for clarifying, Becky. Any other questions on that? Okay. And you know what, actually, before I give you example 1, let's draw out like a general. So I've given you this general series, actually. Let's add a little bit to this at the top. All right, so if you're thinking about this as being your infinite series, which I've just defined for you, these values here that you're adding together, give you a little bit more terminology here. These are going to be your partial sums. And then we can use this to talk about example 1. So the partial sums are just these terms in the series that we're adding together. And then the nth partial sum is what we would get if we were to add them together. So the partial sums would sum to S sub n. Now, remember that when we were talking about sequences, your book used a little s to denote when we were looking at special terms for sequences, and then they switched over to a. But for sequences, we use the lowercase s. For sums, we use an uppercase s. I know for s's, it's kind of hard to tell the difference between an upper and a lowercase. In the end, it really doesn't matter. You're not going to be using this notation very often. But big S sub n is going to be the nth partial sum. Okay, so I'm going to give you an example, and we're going to sort of look at the way the series works, and then we'll talk about some convergence or divergence of a series, what we're going to look for, and what's going to happen with the partial sums and the nth partial sum.
Just quick question. So all the a sub 1, 2, 3, etc., everything sums up to a sub n, or sums up to s sub n.
Yes.
Okay.
Yes. Yep. And then of course these can keep going just because you don't have to stop at n. It's going out to infinity. So this is assuming that you were to stop it somewhere, and these are your partial sums s sub n. Okay, so let me give you example 1. We'll sort of look at how this all works, and then this is going to be the only example that you're going to see like this. From now on, after this, we're going to be talking about special types of series that all sort of work together. All right, so this is the sum from, I just did it, k equals 1 to infinity. And the series is 1 over n times n plus 1. Okay, so this is actually a special type of series I'm going to talk to you about in a couple minutes. First, I just want to use this to really illustrate the way that the series works and sort of put the terminology together. So if I was looking at sums of the series, I could look at, for instance, big S sub 1. That would be the sum for the first term. Now, really for the first term, you're not adding anything together. If it's S sub 1, well, we're letting k be 1, and this is 1 over 1 times 1 plus 1, which is a half. But as you start to work your way through the sums, the goal here is with an infinite series, like there's going to be some sort of pattern that emerges in many instances, especially for this type of series. When you work your way into S sub 2, well, now you're taking the k sub 1, the k equals 1 term, and you're adding that to the k equals 2 term. So we're going to add that to the term that we get. You know, you guys, I might as well just stick with n's because I don't think I'm ever going to remember to switch all these to k's. They're k's. Sorry about that. Okay. So if we let k be 2, so this would be the k equals 1, which we would just discussed. The next term would be what happens when we let k equal 2. So we would say 1 over 2 times, and then 2 plus 1. And then we would simplify that. So 1 over 2 times 3 is 1/2 plus 1/6. And when you add these together, you get 2/3. Now, that's a lot of work just to get to the second partial sum. So right now, if you're thinking about what these are, this is just the second partial sum, 2/3. So anytime you're adding up just particular terms of your series, that's what you're obtaining partial sums.
So you'd have to do this, like if you do it like 10 times, that's a lot of.
Yeah, it depends. So it kind of would depend on your series. And like I said, this is the only one that I'm going to show you where we're actually pulling out these partial sums. And the only reason I'm doing this is because I want you to sort of get an understanding of what a series does and kind of connect it together with the verbiage and the terminology behind it all. So if you were to do S sub 3, that looks like a lowercase s. Make it bigger. You would be taking the first partial sum, and then you would be taking the second one, which we said was 1/6, and then you would be adding that to the third one. So this would be the k equals 1, k equals 2, and then you're letting k be 3. And then this would be the third partial sum. So the third partial sum is not just the third term of the series, it's actually the sum of the first 3 terms. So you'd get 1/2 plus 1/6 plus 1/12. If you hear screaming, they're leaving soon, I promise.
Or you could have just taken the 2/3 instead of adding the 1/2 and 1/6. Okay.
Yes, yeah. So yes, technically, since you already have that, you could do that. I was just sort of building it out, but
Okay.
but you can sort of maybe at this point you'd be like, all right, so I have 1/2, 2/3, 3/4, and possibly at this point you might start to think that you can see a pattern emerging. And so much of what's happening in this chapter is just being able to recognize when you can actually make a conclusion regarding a pattern of behavior. So if you were to do S sub 4, again, K sub 1, K sub 2, K sub 3, and then you would add it to the fourth term in your series. So let's see, you have 4 times 5, and you would add 1/20th to that, and then you would end up with 4/5. So notice what's happening to your nth partial sums. So you went from 1/2 to 2/3 to 3/4 to 4/5. And what I'm hoping that you're seeing here is that in each instance, your numerator and denominator are increasing by 1 value each time. Now, that might not seem like a big deal because no matter what, you're always going to have a proper fraction. However, you went from 0.5 to about 0.67 to 0.75 to 0.8. And if you know that your numerator is always going to be 1 less than your denominator, then you can make a conclusion regarding the kth partial sum of your series, or wherever you decide to stop off making your summation. So we can go ahead now and make a conjecture and state that S sub n for our nth partial sum would have to be equal to n divided by n plus 1. If you wanted to call it S sub k, that's fine. It does not matter in this case because you're just coming up with a general formulation for, like, let's say we let n be this value. Let's say we let n be that value. Whether it's k or n in this instance is not going to make a difference. This is just giving you a general form for your nth partial sum. So this, in our case, would be the nth partial sum. So if we were to sum this all the way up to n, well, I mean, where this came from was really the fact that you're taking the subscript here, and that's the piece in your numerator, and the piece in the denominator is always 1 more than that. So if this was S sub 2, you have 2 over 1 more than that. S sub 3 is 3 over 1 more than that, so on and so forth. So S sub n is going to be n divided by 1 more than that, and you get this nth partial sum. Now, to sort of build on this idea, before I do that, does anybody have any questions here? The idea here is that if we take the limit as n goes to infinity, so if we know that all of our sums are summing to this value, and we're wondering, well, like, what happens to the terms in this series as n gets increasingly large, we can let n get increasingly large, and we can send it off to infinity, and we can look at the limit of our nth partial sum. And if you want to use L'Hopital's rule, that's fine. Or if you just want to use that rule from algebra that says if the degrees are the same in the numerator and denominator for a rational expression, then you take the ratio of the lead coefficients and you'll get the limit to be 1. which means that your series would converge to 1. So I'm going to formalize this next for you. But I hope that you sort of have an understanding now of how the series works and sort of how these terms end up working together to give you such a conclusion. And like I said, it's not going to be in every case that it's going to be so clear like this. I just wanted to use this example to really just illustrate the way the series works. And, you know, you can see how these values are just going to keep getting closer and closer to 1 each time. We kind of talked about the 1/2, 2/3, 3/4, and, you know, 0.75 up to 0.8. Eventually, you're going to get to 1 if this thing keeps going. So let me give you a definition here, or a theorem, actually. Nope, technically it's a definition that sort of correlates to this example. So you can kind of see the way that it is formalized. Convergence or divergence of an infinite series. I'm actually going to back up slightly. Okay. If the sequence S sub n of partial sums so this is just that sequence of S sub n, your big S sub n. If the sequence of partial sums of an infinite series and your series goes from 1 to infinity of a sub k is just whatever that function is inside the series, has a limit s, then the series converges and is said to have the sum s. Now, actually, this is a good conclusion that we were able to come up with. And a lot of the instances that we're going to deal with after this section, you're not actually going to be able to come up with the sum of a series. All you're going to be able to do is make a conclusion regarding its convergence or divergence, whether you can come up with the sum or not. A lot of times you won't be able to. In this case, we did. We said that we could sum up these nth partial sums and get up to 1. That is if the limit as n approaches infinity of s sub n equals s, that sum, then your series from k equals 1 to infinity of a sub k is a sub 1 plus a sub 2 plus a sub n plus blah, blah, blah is equal to that sum s. Okay, now if you end up taking the limit of your sequence of partial sums as n goes to infinity, and you obtain a value of infinity, then the infinite series diverges. Also, if the limit does not exist, we would say the infinite series diverges. Okay, now I'm going to give you another example of a special type of series. I don't actually have a definition for it. You sort of have to recognize it when it pops up, and I'm going to try to help you recognize it by giving you some pointers on how you might recognize this first special type of series you're going to have to deal with. Before I do that, does anyone have a question on this definition for convergence and divergence of an infinite series? Wonderful. Okay, I am going to straight up just tell you what type of series I'm going to give you next. And I'm going to, like I said, try to give you some pointers for how you're going to recognize it. I guarantee you will see one of these on your test. So you should probably highlight it or something. I'm even going to write it in all caps. Telescoping series. Now, this is a special type of series. When you see it, you will be able to come up with the value for the sum. After this, I'm going to talk about geometric series, and you will be able to come up with the value for the sum. After this, once we get into section 3, you're not going to be coming up with any values for sums anymore. You're just going to be making conclusions about convergence or divergence. The special series I'm giving you right now, you're going to be able to come up with sums for. Now, actually, the series I gave you in example 1 was also a telescoping series, but I didn't use the method of the telescoping series to show you that. I mostly just picked it because it's a good one to be able to detect that pattern, the pattern of behavior. So in its simplest form, a telescoping series will look something like this. Let's see, we're going to go from k equals 1 to infinity. Like I said, we usually start at k equals 1. And it usually, if it's in its most obvious form, will be written using two terms, and some sort of subtraction will be involved to get from one term to the next. So this one is the series from k equals 1 to infinity of 1 over k plus 1 minus 1 over k plus 2. So I'm showing you this one because I want you to recognize what a telescoping series will look like generally. And then I'm going to show you some where you're going to be given a series and you're going to have to turn it into a telescoping series. So that's the harder one because you're not going to know what to do with it at first. Okay, so with the telescoping series, what I want you to recognize is that if you start writing out terms of your series, you are going to see something special occur, and that's because of the minus sign that you have between your terms. So start out by letting k equals 1. So if k equals 1, you'll have 1 over 2 minus 1 over 3. I like to group these together so that you can very clearly see what's happening. Okay. And then you can add that to the next term in your series. So that happens when k equals 2. So if we let k be 2, we have 1 over 3. So we'll have 2 plus 1, which is 3, minus, and then again, if k equals 2, now you'll have 1/4. I'm going to go through a couple different terms of this series just so that you can really start to see what's happening with the terms. If we let k be 3, well, 3 plus 1 is 4, 3 plus 2 is 5. But I think this is probably sufficient to really help you to see what's going on. I'll do one more. If k is 4, we'll have 1/5 minus 1/6. So what's going to happen here is you're going to keep adding.
You said 1/5.
Together.
That looks like a 6.
It's a 5, but I'll rewrite it for you. You know, sometimes it's always the 6s that in algebra, anytime I write B, students are like, is that a B or a 6? It's a 5. So what this is going to do is it's going to keep going until I end up getting at some point to some nth term or some kth term, if you will, call it whatever you want, where we get to 1 over k plus 1 minus 1 over k plus 2. What now you can start to see, however, that in each one of these terms, you have an additive inverse that's going to cancel out with one of the terms in the next set. So if I'm looking, for instance, between k equals 1 and k equals 2, I'm seeing I have negative a third plus a third. Those are going to cancel each other out. Negative 1/4 plus 1/4. Gone. I even think it might be most instructive if we include the n minus 1th term. So let's call this n instead of k. I'm going to rewrite this. I think it'll be most clear. I mean, you can call it k if you'd like. You can switch it to n. It does not matter to me. All right, so let's say we're looking at the, instead of the nth term, let's do the n minus 1th so that we can start to see things cancel even on the other end. So if I let this be n minus 1, I'll have n minus 1 plus 1, and then n minus 1 plus 2. And then the last two terms are still going to be 1 over n plus 1 minus 1 over n plus 2. So on and so forth. Now, n minus 1 plus 1 simplifies to 1 over n, and n minus 1 plus 2 simplifies to 1 over n plus 1. So this term right here is the n minus 1th term. And this is the nth term. But you can see now that this behavior continues not just in these first few terms of your series, but as you work all the way towards the end. So negative 1/5 plus 1/5. Now, even though I didn't show the plus 1/6, you can ensure yourself that it will be there. You can also see that this term right here is 1 over n plus 1. So is that. This one's the minus version. That one's the plus. So those two are going to cancel out. This one is going to cancel with something that came before it. We just don't know what it is yet. But what you're going to see here is that this behavior sort of works its way from the outside in. I mentioned this last week with something else, and I don't remember. I said it's sort of like a telescoping series. And I was like, wait, we haven't talked about telescoping series yet. I wish I remembered what it was. But what you're seeing happening is that there's going to be this symmetry between the cancellation of the first couple of terms and the last couple of terms. So all you're going to have left in the end is 1/2 minus 1 over n plus 2. Everything else in between there is going to cancel. And if you don't believe me, go ahead and write the n minus 2 term, and you can start to see stuff is going to cancel out still as you work your way backwards from the right. But now you can actually write this as your sequence of partial sums, S sub n. And we can say that S sub n is really just 1/2. Oh, not plus, it's minus. Minus 1 over n plus 2. And then we can take the limit of this to figure out the value to which the series will converge. So we're going to take the limit as n approaches infinity of 1/2 minus 1 over n plus 2. And the limit of 1/2 as n approaches infinity is 1/2. And then as n approaches infinity, the limit of this ratio is going to go to 0. So your limit here is 1/2. And I think that should be pretty intuitive. I mean, think about the fact that as we continued on writing terms of the series, you could see that the denominators were getting increasingly large. And eventually this denominator is going to head off to infinity, which means your ratio is going to head off to 0. So this means that the series converges and the sum is 1/2. Now, I usually give some trickier examples for this. Your book does not give any tricky example homework problems, so I'm going to keep it a little bit more basic here. But I do want to show you one of these telescoping series that's written in disguise. Before I do that, does anyone have a question on example 2?
Nope.
So example 3, I'm going to tell you right now that it's a telescoping series, and I'm going to show you how to rewrite it so it looks a little more obvious. So example 3 is going to be the series from k equals 1 to infinity of 1 over 16k squared plus 8k minus 3. Now we're going to get all the way to the end of this chapter, and eventually you're going to take an exam, and I'm going to tell you to give me the sum of the series. And you might not remember that this is a telescoping series. I'm not going to tell you that it is. But if I'm asking you to give me the sum of a series, it can only be a few different types. It's going to be either telescoping or it's going to be geometric, which we're going to talk about next. Otherwise, I'm only going to ask you if the series converges or diverges. So one hint for your exam is if I'm asking you to find the sum of the series, it must be either geometric or telescoping. It has to be. So if I gave you this and you were like, I can use a comparison to tell you if it converges or diverges, and then you use a method from later in the chapter, that's fine. But if I'm actually asking you for the sum, you need to figure out how to do that using a telescoping series in this case, because this is not going to be anything like a geometric, which you're going to see next. If you're trying to figure out how to write this as a telescoping series, remember that what we're really aiming to do is write this so that it looks like the difference of two rational expressions. So thinking back to what example 2 looked like, it's kind of a specific form that you're going to see for the telescoping series. We had a rational expression minus another rational expression. In order to get it to telescope, we need to have this issue where we're going to be subtracting off other terms that come later in the series. You're not going to get that unless you rewrite it in this form. I mean, I don't know, it's possible, I guess, maybe that you could some students have very good number sense, and they'll go through terms of the series and they might eventually find a formula for S sub n without actually going through this process, but I would find that to be a little questionable if one of you did that for something as complicated as this. You're like, I don't know, because it's very complicated, as you're going to see. All right, so first you're going to factor this. 16k squared plus 8k minus 3. In order to factor this, use the AC method or use the box method. I don't care how you factor. It's Calc 2. You factor however you want. In order to get to negative 48, the numbers that I'm going to use are, let's see, not 24 and 2, not 16 and 3, 6 times 8, no, 12 and 4, negative 4, positive 12. Because remember, I need these to add to 8. I feel like I'm giving a factoring review right now. Okay. I'm going to rewrite the middle term as plus 12k minus 4k minus 3. And I'm going to factor out the GCF to do factor by grouping. I'm going to pull out here a 4K, and that leaves me with 4K minus 3. I'm going to pull out a negative 1, which is going to, oh, plus 3. Where it comes from. 4K minus 3. Okay. And my terms now are 4K, or my factors are 4K minus 1 and 4K plus 3. Some of you do guess and check. Some of you do the box method. Whatever you need to do to factor where your lead coefficient is something other than 1. Do whatever you need to do. 4K minus 1, 4K plus 3. Okay, so this is half the battle. If you have a trinomial, and that's how your denominator will appear if you have a telescoping series in disguise, it's going to be in the form of a trinomial. You're going to factor it. And then if you're trying to rewrite this as the difference of two rational expressions, the only choice you have available to you is to use partial fractions. So we're going to use partial fractions to write the expression as a difference. Now, it's not going to be really clearly obvious to you at this point that you're even going to get a difference. I'm not going to give you one of these to do if it's not going to turn into a difference. If it's a sum, then you're not going to get your terms to cancel, and then there's no point in me even giving this to you at all. All right, so back to our partial fractions. We're going to write this as A over 4K minus 1 plus B over 4K plus 3. Before I continue, does anyone have questions? I didn't realize we were dwindling down so much. I guess I shouldn't be surprised, but I didn't really look. I'm only looking at little rectangles with your initial on them. Except Jenny, I actually have a picture for. It's close to you being on camera.
Yeah, we do have quite a few less people here.
We didn't start out with a full class to begin with, but it's a rough semester, you guys. I feel for you learning Calc 2 like this. I'm trying to make it as much like a normal class as I can, but Calc 2 is not easy no matter what. And when you're trying to get tutoring online and come to online office hours, I get it. You're kind of just like, this sucks. So hang in there, the few, the proud, the 11. All right, let's do some partial fraction expansion. Okay. 1 equals A times 4K plus 3 plus B times 4K minus 1. You pick whatever value you'd like. I'm kind of trying to isolate A here. So if I wanted to do that, I could let K be 1/4. 4 times 1/4 is 1, minus 1 would give me 0. So I'm going to do that first. 4 times 1/4 again is 1. And I would get A equals 1/4. And then I'll do something similar for B, or you can just plug in A and solve for B at this point, but I'm going to let K be equal to negative 3/4. So I'm trying to get a negative 3 here, so I can do negative 3 plus 3. And then I'll get B times negative 3 minus 1. So negative 4, B equals 1, and B equals negative 1/4. What the heck? All right, so that was a method that you learned back in chapter 7 if you did not learn it in algebra. So let's rewrite the series now from 1 to infinity. Remember that I initially had a trinomial. We rewrote it as the factored variation. Luckily, my A term was positive, and that was the first one. B was negative. If you ended up getting that to be opposite, it's fine. I probably would switch the terms just because I like it to be written as a subtraction instead of a negative plus a positive value, but that's up to you. So you have 1/4 divided by 4k minus 1 minus 1/4 divided by 4k plus 3. Just turn the plus into a minus instead of writing it as plus negative a 4. And then if you don't like the complex fraction, that's fine. You can just put that 4 into the denominator and write it factored. This is about as complicated as the rewrite is going to get. I should have even checked to see if your homework was going to give you anything with a trinomial. I just assumed it would. But then also last semester, I assumed they were going to give you different types of cancellations, and they did not. So nothing is poking out, but it could come up later. I see some quadratics that are not trinomials. They're just factorable, like difference of 2 squares kinds of things. Oh, well, it's fine. You understand the process. You've seen it. Okay, so the goal here is to get you to recognize something as being a telescoping series, even though I'm not telling you it's a telescoping series. So if I say find the sum of the series, and the series looks like this, or it's got a constant in the numerator, and the denominator is some sort of quadratic expression, or it's some sort of factored expression where you have linear factors, or it's presented to you like this, where you have a difference of 2 rational expressions. Those are the 3 ways that you're going to see a telescoping series present. So you're looking for one of these. If you don't have it, you're going to rewrite it, get it to something like this where you have a difference of terms. Technically, I should have brackets around this. I do not, but technically I should. I get a little lazy with the brackets, which is weird because I usually don't in other sections. I don't know what it is with the summations. I'm very good about them with integrals. All right, so let's go ahead and start writing out the terms of our series so that we can see what's going on with them. I can tell I'm going to need my calculator right now. First, I'm going to look for the k equals 1 term. Then I'm going to add that to the k equals 2 term, so on and so forth. So if k equals 1, I'm going to end up with 4 minus 1, which is 3, times 4 is 12, minus 1 over 28. And this is what we get when k equals 1. And then we'll see what happens. Hopefully we see the canceling right away. Sometimes it takes a term or two. Like I said, I'm not giving you anything too crazy here because your book didn't give you anything too crazy. So I decided why go for a crazy example if we don't need to. If we let k be 2, 2 times 4 is 8, minus 1 is 7. 4 times 7 is 28. And there is your 1 over 28. Now, if you let k be 2, 2 times 4 is 8, plus 3 is 11, times 4 is 44. And you're going to just do another term or two just so that you can verify that this behavior is going to continue. I wouldn't stop yet. Show me a little bit more. Let k be 3, and you'll also then get 1 over 44. And at this point, you could start to really justify that pattern. 3 times 4 is 12, plus 3 is 15, times 4 is 60. And I would say this is pretty good in order to justify what's going on with the terms here. If we were to write out the nth term, it would look like that. So the whole point of a telescoping series, like I said, is that you see this symmetric behavior as far as the cancellation is concerned. So if we are looking for symmetry here with our cancellations, We know that the first and the last term are not going to cancel. They're going to stay right where they are. Everything in between, though, is going to have an additive inverse, which it's going to cancel out with. So what you're going to be left with is this sequence of partial sums that is of the form 1/12 minus 1 over 4 times the quantity 4n plus 3. And then you can write out your limit in order to get that sum. I mean, really, technically, you can see the sum just by looking at it. On your test, I will give you points for writing out your limit. It's really just one little thing you have to do. I know you're like, isn't it obvious? Yes, to me it is, but I want to make sure that you know what you're doing. So your series is going to sum to 1/12. So if you took all the terms of your series and you added them together, eventually that's where they would head. I was just thinking about this. Gosh, I haven't done this sort of thing in my calculator in a really long time. I could not remember how much work your calculator did as far as summing up series. I know that it does, but I don't think it takes them to infinity. I'm just looking at mine right now, which of course you can't see, of course. If you're wondering how I got there, if you just want to play around with the menu a little bit, mine is of course a template. If you have an older one, you're going to have to use commas to separate out your arguments. I got it from going to the math menu, and then I just scrolled up instead of down, and then the summation is 0. And then you can, choose your index. It's, I think, set to alpha. So I'm just going to pick K by hitting the parenthesis. And then let's say I start at 1. I'm just curious to know if your calculator does this. I can't remember. But you know what? I don't think yours goes to infinity. I just don't think it'll do that. And even if it did, I never used this calculator when I'm using infinity. I think it might be in the catalog. It might be in your number menu. I don't know. I was mostly just seeing if you wanted to play around with this and stuff. But maybe this is more complicated than I had anticipated. You go to your catalog, which is second 0. It might not even have infinity because there's no. Yeah, I don't think it does. Never mind. Technically, you could take it up to like maybe 10,000. See if you can get close to 1/12. Just take it up to some really large number. 10,000. I don't know. Just thinking if you wanted to check your work. 16. Gosh, I don't even know if it will do this. Alpha is K squared plus 8K minus 3. I don't know what to expect here, you guys. Oh, I've really confused it. All right, maybe checking our answers in the calculator wasn't our best choice. If you can come up with a better way to do it, let me know. It's very confused right now. I'm going to let it simmer. Okay. So that was a telescoping series. I do want to define for you something called a harmonic series. Oh, I really want to make sure that I don't forget to cover this because we're actually going to see this series a lot. I just want to mention it. There's not a lot we're going to do with it right now, but it pops up in this section. If I don't cover it here, I'll end up somehow glossing over it. Definition, and then we'll talk about geometric series after that. harmonic series. The infinite series, k equals 1 to infinity of 1 over k. This throws people off because in 8.1, when you guys were talking about sequences, you looked a lot at the sequence 1 over n. And when you did that, you got very used to this idea that the sequence converges. And that's true. The sequence does converge because as n gets increasingly large, if I was looking at this as a sequence, this value, I'm just writing out term after term after term, is eventually going to go to 0. But that is not the case with the harmonic series. This starts at 1 and it goes up, and you keep adding, you know, a half, a third, a fourth, blah, blah, blah. This is called the harmonic series. We're gonna, like I said, we're actually gonna use this series a lot throughout the chapter, especially as we get into later sections and we work on finding comparisons. This is gonna be a series that you're gonna go to a lot as one that you know diverges. Theorem, the harmonic series diverges. Don't get your harmonic series mixed up with the sequence 1 over n. The series itself diverges. You're just adding too many numbers to the 1, and it's not actually going to converge to a value. And I know that seems odd because you're thinking, well, eventually at some point it has to. If you really want to, on page 597 of your text, there's a proof for it. Feel free to look at it. Your harmonic series diverges. So we're not going to use it a ton today, but it's in this section, so I wanted to make sure to mention it. Oh, I got a syntax error eventually in my calculator. Such is life. Okay, so the other type of series we're going to talk about in this section is the geometric series. Before I do that, does anybody have a question so far?
Are you going to show us our harmonic series example?
No, because this is like the harmonic. This is it. This is the harmonic series. So
Okay.
we're gonna use it later a lot, in conjunction with other series. But as for right now, I'm just presenting it to you. I think it's a little bit weird actually that it pops up in this section. I would have put it in the next section when we actually talk about series with positive terms. But it's here. So I just did mostly I wanted to put it here because your book put it here and I didn't want to forget to mention it to you. So no, for right now, I'm just going to leave this here for you for later. Okay. Geometric series. Definition. This is a biggie. This is another one that we're going to use a lot today, but you're going to use a lot again later. Telescoping series, you're not going to see after this section unless it's in a review. The nice thing about this particular chapter is that each section gives you like review problems from the previous sections. Not so much sequences, but when it asks you for convergence and divergence, it'll throw in stuff from previous sections, which is really nice to help keep you current for your exam. But telescoping, you might see pop up in some sort of review segment. You will not see it really again after this. Geometric, we're going to be using all the time throughout this chapter, all the way through the chapter. Geometric series. You first learned about these in algebra at some point. You learned about arithmetic and geometric sequences and series. Geometric series. So this might look very familiar to you when I write out the definition. You're going to see this in the form k equals 0, and it's very specific here that k equals 0 to start. Now, technically, you don't have to start it at 0, but if you start it somewhere else, you're going to have to correct for that inside your formula. So, for instance, if you start this at 1, then you need to account for that by then taking k minus 1 away. So no matter what, you're looking for your first term to have r to the 0. So if you start at 1, you need to correct for that so that your first term is r to the 1 minus 1 is 0. See what I'm saying? So this is equal to a plus ar plus ar squared plus yada, 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 ar to the n minus 1. And that just keeps going and going and going. So this is your geometric series. Let's see, the series of the form blah. And I'm going to say a cannot be equal to 0 because then you wouldn't have a series to worry about. And r is your ratio. We're going to be doing a lot of work with this ratio r and just kind of pulling it out of your series and then talking about how r deals with convergence and divergence. So I'm going to give you a theorem right now that talks about the convergence of a geometric series. And then we're going to do a bunch of examples where not only are we looking at whether or not the geometric series converges, but we'll be talking about getting an actual value for the sum of the series if it does converge. So this will be theorem, convergence of a geometric series. So you have two conditions. The first one is that if your ratio r has an absolute value that's less than 1, the geometric series converges. Converges. And its sum is the sum for your series k equals 1 to infinity of a times r to the k minus 1 is going to be equal to a over 1 minus r. Now, I'm going to give you a bunch of examples of this, but it's very important that we note that a is going to be the first term of your series. Okay, because you're going to see that if that index switches, I don't want you to just automatically pull out a. I want you to actually think about the first term of the series. So for instance, if we started at k equals 2, well, then we'd actually have to take a times r to the first power, and that would change the first term of your series. But assuming that you started at 1, then a would be your first term. But no matter what, a is going to be the first term of the series. And like I said, I'll give you some examples where we'll switch the index and you'll have to account for that. If the absolute value of r is greater than or equal to 1, the geometric series diverges. You are going to just have to remember the conditions for this, but hopefully, because we're going to be given a lot of tests and a lot of different things you're going to be doing throughout the chapter, and you're probably going to create for yourself some sort of cheat sheet to use on your exam. Otherwise, everything's going to be all over the place. This is definitely something that you would put on your cheat sheet. This is something, like I said, you're going to use this in every single section. This is outrageously important. You're going to use this series a lot as a comparison when we work on comparison series, and you're going to be using these again even when we work on power series, just rewriting everything in terms of geometric series. So this is outrageously important. If the ratio is less than 1, so some sort of proper fraction, or some decimal that's less than 1, then you can go ahead and safely say that your geometric series converges. If r is 1 or greater than 1, or less than -1, in that case, the geometric series diverges. So it doesn't matter if r is negative or positive. What you're looking for is the absolute value to be either less than 1 to converge or greater than or equal to 1 to diverge. So let's talk about some examples using geometric series. This is example 4. I'm going to give you some instructions here. Determine whether the series converges or diverges. If it converges, find its sum. So like I said, the only time I'm going to ask you to find an actual sum of a series is if I give you a series that is either telescoping or geometric. After this section, you're not going to be able to give me a sum. You're just going to tell me whether your series converges or diverges. Unless it's geometric. Because you will see those peppered throughout. Okay. I'm just going to just do a series of examples here. A series of examples with the geometric series. The first one is going to go from 0 to infinity. And the series is going to be -1 to the k times 5 divided by 4 to the k. Now, a lot of times when you see a geometric series, it might not always look like a geometric series, very similar to what you see for a telescoping series. And you're going to have to rewrite it to be in the form of a geometric series. So what you can do, and it's kind of up to you exactly where you want to put everything and how you want to rewrite it. But the goal here is that we want to have a ratio to the kth power. If you want to leave the 5 in there, that's fine. But we're going to use some rules for exponents here in order to combine these and get them in the form that we need. So I can rewrite this by saying that I have the series from 0 to infinity, and I can write the fraction -1 to the k over 4 to the k as the ratio -1/4 to the k. Now put the 5 in front if you'd like, and now you have AR to the kth power. If you're going back to your definition on geometric series, this is exactly what you are looking for. Fit it all in here. We are looking for the series, and in our case, we're starting at 0, but we have A times R to the K. R is a ratio. We've just rewritten this now in the form of a geometric series. Okay, So what you're going to do first is you're going to determine whether your series converges or diverges. Before I do that, though, I just want to make sure, does anyone have a question about how I rewrote the series? Okay. Wonderful. All right, so we're going to pull out R in this case, and we're going to say that R is -1/4. But we know that -1/4 has an absolute value that is less than 1. This means that your geometric series converges. And sometimes I feel like that happens so fast that students are like, wait, what? Don't we have to meet any other conditions? Like, that just seemed too simple. Listen, as long as you're in this form where you have A times R to the kth power, all you need to do is focus on R. The value of R is going to tell you whether your series converges or diverges. If the absolute value of R is less than 1, it converges. If the series converges, you need to give me the sum. So that's what you're going to do next. I wrote down that the sum, and when I gave you the formula, it went from, remember what I gave you, it went from 1 to infinity. I know you just wrote it down, but for me, it's on another page, and I wanted you to be able to see it right in front of you, is A over 1 minus R. Now, it does not matter that we started our series at 0 instead of 1. What we're going to do in order to determine the sum of the series is we're just going to take the first term and we're going to divide it by 1 minus R. Well, in our case, anyway, if we're talking about the first term starting with k equals 0, if we're taking a quantity to the 0 power, any real number to the 0 power is 1 anyway. So A in this case is in fact going to be the exact first term of the series. So we can say that for our series, A is going to be the first term. And again, just, I wouldn't necessarily follow this formula exactly. I would always double check the first term. If k is 0, the first term is 5, and then 1 minus R. R is -1/4. And then you'll just simplify that quantity. 1 plus 1/4 is 5/4. And then if you're dividing by 5/4, you're multiplying by 4/5. And 5 times 4/5 is 4. There's not necessarily a great way to check your work per se, but you can always start to write out some sums of your series. I'm sure if you put something in your calculator that didn't go up to 10,000, you could start getting some initial sums and start to see that they head to 4. And then, if it looks like they're starting to get close, then you can say, okay, I'm sure I must have done this correctly. Everything's good. But really, I don't find that students have too much of an issue with these geometric series. They're usually pretty straightforward. Sometimes I get students who come to the office hour not sure how to simplify some of these. So I want to make sure to go through a bunch of different types of examples where you're going to see a bunch of different things. And hopefully that'll help you as you work through your homework. I'm going to give you another example on this, but does anybody have a question on this one?
I have a quick question.
Yeah, go ahead.
So the formula was k equals 0, and we started out at 1, but we didn't have to change anything because...
Oh, because we still were just taking this ratio to the 0 power. So this formula adjusted for the k equals 1 because they took away 1 from the exponent. But we still had a 0 exponent. The only time you'd have to really change your first term would be, let's say, if we had a k here and then k started at 1. Then your first term would be like 5 times -1/4 in that case. that make sense?
Yeah,
Okay, we'll do some where we have to adjust.
cool.
So don't worry about that. Example 2. Sometimes you'll see these with decimals, and then your life will be as easy as it could possibly be as far as your geometric series are concerned. You don't even have to worry with the decimal about wondering what's happening with the fraction, even though these fractions are usually pretty straightforward. All you're looking at is what is happening with the ratio. In this case, A is 1. You don't see it written because we don't usually show multiplication by 1. We're just taking 1.1 to the kth power. R in this case is 1.1, which is greater than 1. And this should be one of the fastest Calc 2 problems you're ever going to do. You're going to tell me that the series diverges. And then you can't tell me the sum because it diverges. You can't actually find the sum here. Okay, so we're just looking at the ratio. Nothing super tricky is happening. Questions there? Okay. So for C, we have another instance where we have a series that's in disguise. So this one is not screaming out geometric series at you. And if it is, be careful. The reason I would tell you to be careful is because you don't have, in this case, A times R to the K. You have a negative K. And in order to rewrite this, you're going to have to make this K positive. So you can do a little side work if you don't want to keep writing your sum. I know sometimes students don't want to do that. We can write e to the negative k as e to the negative 1 to the kth power. There are a couple different ways of doing this. You could also split up your base. I think this is the easiest way of doing it. Remember, when you take a power to a power, you multiply the powers. And then e to the negative first is 1 over e. It's nice to have this written as a ratio. As you saw in the last example, it does not have to be written as a fraction. But I mean, technically, you could leave it like this if you wanted to. This is also fine. I think if it does end up converging, it's going to be easier to use this to find the sum, which is why I tend to not leave negative exponents if I don't have to. All right, so you're going to rewrite your series from 0 to infinity as 1 over e to the kth power. And you're going to get used to seeing this one. I don't know, it's kind of popular. It pops up a lot. If you're trying to find 1 over e in your calculator, just write 1 over and then enter e to the first power because it always wants an exponent on that. And you'll get approximately 0.3679. So your ratio is indeed less than 1. If you want to write it as the absolute value being less than 1, that's fine, but you don't need to include the bars. All you need to know is that your ratio is less than 1. And if that's the case, we would say that the series converges. If your series converges, you need to find the sum. And again, you're in a situation here where you're starting at 0 and you're going up to the kth power. So the 0th term is just going to be 1 over e to the 0, which is 1. So your sum is just going to be the first term, which is 1, divided by 1 minus r. And then you'll simplify that. So don't leave it as a complex fraction. Simplify it out. Multiply every term by e. That's better. And leave it exact. I know sometimes we don't like working with these transcendental numbers, but leave it exact. Questions on C? D, this is going to be the series from 2 to infinity. So we're switching up the index this time of 3 times negative 0.75 to the kth power. Now, it does not matter. Like I said, your index is not going to make a difference here. You could always correct for it anyway, so it does not matter. What you're focusing on to determine whether your integral converges or diverges is R. And you would say that the absolute value of negative 0.75 is less than 1. So we would say that the series converges. And then you would have to list out the value to which it converges. My suggestion for you would be to actually compute out the first term. And I also would probably suggest that instead of writing this as a decimal, you convert it to a fraction. I'm more comfortable working with fractions, but that's up to you. So to find the sum, you're going to take the first term divided by 1 minus r. So your first term is going to include the 3, and then it's going to be negative 3/4 to the second power because you're starting at 2. And then you're going to divide by 1 minus negative 3/4. I mean, you could always do this in your calculator and then just, use the fraction button to simplify it. That's up to you. That is up to you. When you square a negative number, it becomes positive. 3 squared is 9. 4 squared is 16. And then 1 plus 3/4, 4/4 plus 3/4 is 7/4. And then just simplify out your fraction. You'll have 27/16 divided by 7/4, which means you'll have 27/16 times 4/7, which is 27 out of 28. Leave it exact. If you put that in your calculator, you're going to get a weird decimal approximation. If you do that, turn it back into a fraction. I mean, I'm assuming you originally got the decimal by just popping that in. If you do put that in your calculator, make sure you're using all the appropriate grouping symbols. The negative would have to be on the 3/4 in parentheses before you square it. That sort of thing. Questions on D?
Nope.
Let's do a couple more. Some of the ones in your book are going to be a little bit harder to simplify, like what you're going to see with E. So we're going to go from 1 to infinity of 3 to the k minus 1 divided by 6 to the k minus 1. And I'm going to do the work for this off to the side, just because I don't want to have to keep writing out my summation. So the first thing you want to do in this case is you want to split this up into two fractions using that common denominator. That would be my first suggestion to you. So split it up using the LCD. That's very important. Remember, you can't just pull the one out because the one technically has this denominator on it. And there are a bunch of different ways that you can simplify this. Since you know you're going for writing this as a ratio to the kth power, my suggestion to you next would be to write this ratio so that you have the entire fraction being taken to the k minus 1th power. Now, if you don't remember your rules from algebra, this is going to be a hard thing for you to do. So I'm hoping that with these examples, I'm refreshing your memory. Now, this one might be odd for you. Watch this. You might be like, wait a second, the one didn't have a k minus 1 on it. But it doesn't matter. You can take 1 to a power and you're still going to get 1. So you should just write it like that. That would be my suggestion to you. And you can always leave the k minus 1 as your exponent, so you don't need to worry about actually splitting that off. You can if you'd like, but you can just leave it. You can write this as 1/2 to the k minus 1 minus 1/6 to the k minus 1. Now, you are in the form of a geometric series. If I can remind you, I gave you two definitions just, for clarity. I want you to get used to seeing both of them. No, I don't remember where it went. It's gone. Gone for forever. I don't know. But anyway, I'll have to remind you of what it is. Recall that we have the series from n equals or k equals 1 to infinity of a times r to the k minus 1. Remember, if we let k be 1, we should get the 0 power. And that's what we have here. So don't be thrown off by the k minus 1s. They're fine. Let's rewrite the series now. And I'm going to split this up into two different series because I actually have two different things going on. What you can't do is you cannot combine these as 1/2 minus 1/6 to the k minus 1. There is no exponent rule for that. So you have to understand your exponent rules in order to simplify these out. All right, so we're starting at 1, just like we originally were. I'm going to rewrite this as 1/2 to the k minus 1, and then I'm going to subtract off the series from 1 to infinity of 1/6 to the k minus 1. Let's see. You know what? I was going to give you a theorem that said you could do that, but for some reason it was actually in the next section. I remembered writing it down. That's really odd. It's a valid move. But I mean, if you think about it, you're really just summing up the terms anyway. This is just saying that you're adding them and then you're subtracting them off instead of doing it all at once. So it is a valid move. But I will have a theorem for you in the next section for that. Okay, questions so far? Okay. So we would say that in this case, this series converges because 1/2 is less than 1. And this series also converges because 1/6 is less than 1. So we have that 1/2 is less than 1, 1/6 is less than 1. Therefore, our series converges. Now, if one of these terms were to diverge, then the whole thing would diverge when you're talking about summing up two sums. We need everything to be convergent, but we can split it up into two sums, also convergent, as long as each individual component converges. But now we can go ahead and write the sum. So we know the series converges. we can go ahead and write the sum now. If we know we're starting at 1, 1 minus 1 is 0. So I'm talking about my first term being 1, dividing by 1 minus a half, and then minus, again, the first term being 1, divided by 1 minus 1/6. 1 minus a half is a half. 1 minus 1/6 is 5/6. And you'll get 2 minus 6/5, which is 4/5. The next one actually is a little bit easier. Maybe I should reorganize these in the future. This one is F. So this is going to be the series from 0 to infinity of 4 over 2 to the kth power. Now, this series is not supposed to be really hard. The only tricky thing is that sometimes students accidentally rewrite it wrong and do the algebra wrong. It's not the series itself. It's always everything that we encounter in this class is the algebra. Anything that's going to give us trouble. You can rewrite this, however, by just writing the 4 in front as A. And then if you have 2 to the k in the denominator, you can write that as 1/2 to the k. Remember, 1 to the k is always going to be 1. So you can use that to your advantage. Technically, if you weren't sure, you could have always said that this was 2 to the negative k, and then you could have brought your positive exponent up and made it negative. And then you could have split this up again as saying this was 2 to the negative first to the k. And then you would have come to the same conclusion because 2 to the negative first is a half. So it all kind of depends on the way that you're thinking about this. Everyone's going to arrive at these conclusions in different ways depending on how you work with your exponents. All right, but anyway, now it's rewritten. Any questions on the rewrite? Wonderful. We know that R is a half, which is less than 1. So we know the series converges. And then to figure out the sum of the series, if the first term we're going to find by letting k equal 0. And of course, if we just have k and we're starting at 0, the first term is going to be a. So our sum is going to be 4, because we're taking 4 times 1/2 to the 0 divided by 1 minus a half, which is 8. And hopefully, as you work through these, you will find that they're actually kind of fun. I'm not being sarcastic. I think they're kind of fun. See what other forms you might see. I'll give you 2 more. So we'll go from k equals 2 to infinity of 1 over 3 to the k. That one you shouldn't have too hard of a time with. Minus 2 over 3 to the k plus 2. Okay. Now, again, you can split this up however you see fit. I'm going to rewrite mine as 1/3 to the k. So we've used this technique a few times now. And then minus the sum from k equals 2 to infinity of 2 times. And then I can do the same thing here with my denominator. I can say this is 1/3 to the k plus 2. Now, if this is bothering you, which it probably is, split this off. You certainly don't need to have a k plus 2 here. You can do whatever you need to do to the exponent. It's really not going to make a difference. It's more just your comfort level with dealing with this particular expression. You can leave the first one as is. So remember that when you are multiplying and you have the same base, you add the exponents. So you can say this is 1/3 to the k times 1/3 squared. And when you're multiplying with the same base, you add the exponents. That's where that comes from. You're just deconstructing it. So you'll have 1/3 to the k minus, and then 1/3 squared is 1/9. So you'll have 2/9 times 1/3 to the k. Now, it does not matter that you're starting at k equals 2 and you have a k here. You don't need to worry about subtracting 2 and doing anything crazy. We're just going to account for that when we write the first term in our summation. And notice that, by the way, in this case, you're seeing that in both cases, r is going to be less than 1. So if r equals 1/3 and r equals 1/3, the series will both converge. So the series converges. Does anyone have a question here? Wonderful. So let's go ahead and find the sum. So we're going to take the sum of the first series and then subtract off the sum of the second series. So whether you combine it all together or pull it apart, it is not going to make a difference. Here, your first term is going to be what happens when k equals 2. So the first term is going to be 1/3 squared, which is 1/9, divided by 1 minus r. And then you're going to subtract off your first term, which is going to be 2/9 times 1/9 divided by 1 minus r. And then you'll just simplify that fractional expression. So 1/9 minus 2/81 divided by 2/3. 1/9 minus 2/81 is 7/81 times 3/2. Just skip right to the chase here. And you get 7/54. Questions on that one? Okay, I just have one more example for you, so I'll just do 8-3 asynchronously, no big deal. I'm going to do it tonight because I'm totally in the zone. I have a headache anyway. I can't work out on my Peloton when I have a raging headache. H. K equals 1 to infinity. And you're not going to see them get any more complicated than this. So you'll have 5 times 2/3 to the k. That term itself is not going to be a big deal for you. And then minus 7 to the k minus 1 over 6 to the k. I'm going to split off the second term first, just so that we can, I mean, this one we don't have anything to do with right here. It's pretty much done. Stick a fork in it. But the goal here is that I want to be able to rewrite this. And the easiest way to do that is going to be by taking a ratio to the kth power. So I can't have k minus 1 and k and combine these all at the same time. So I'm going to rewrite 7 to the k minus 1 over 6 to the k as 7 to the k. And now I'm going to do that trick again, where when you're when you're multiplying with the same base, you add the exponents. But this time I'm just going to deconstruct it. So I have the same base, I'm multiplying, I can add the exponents. So k plus negative 1 is k minus 1. Now, because I'm multiplying, I can just think about this as being 7 to the negative first, which is 1/7. And then I have 7 to the k over 6 to the k. I'm doing this in 2 steps, but it's something that you would probably do in 1 step. So I have 1/7 times 7/6 to the kth power. Whatever you do, don't cancel out the 7s. You cannot do that. This is not 7. It's 7 to the k. You can't cancel these. Resist the urge. So I'm going to rewrite our problem statement now. Does anyone have a question on how we came up with this expression? So we've had a good run here where we've had a lot of instances where r has been less than 1. Here we have r equals 2/3, which is less than 1. Now we have r equals 7/6, which is greater than 1. It does not matter if all of the terms of this series sum to some finite quantity if this one doesn't. I know you're thinking, well, you're subtracting, so doesn't matter. If you take a finite value and you subtract off something that's infinite, what do you think happens to it? Certainly doesn't converge to a specific sum value. In this case, all we need to know is that one of the terms of this series diverges. If one of them diverges, the whole thing is going to diverge. So we don't need to worry here about finding the sum. 7/6 is greater than 1. Your series is going to diverge. Okay, I don't have time to get started on 8.3. I'll do it asynchronously. 8.3 is all about the nth term test for divergence, which is easy, p-series, which is easy, and the integral test, which is harder. So that's what you have to look forward to in 8.3. And then 8.4 is where we start our comparison tests. So we'll kind of see how long 8.3 takes me. I'll probably get into 8.4 in the async lecture. That's my prediction. All right, but that's it. I will be on until 8:30 for the office hour. If you have questions, I'm going to go right now and put up some homework so you guys can get to work on this. Hopefully it won't cause you too much of an issue with the telescoping and the geometric series. Nothing too crazy here. I don't even think there's any harmonic on here. But if you have questions, stick around. Otherwise, I will see you guys next week. And I hope you have a wonderful week ahead of you. Adios.
Wow, they all jumped off really fast.
That usually happens just with so few students. It's like more start.
Were you talking